Welcome back. So what proof was or is there that the crust, which is broken up into various plates, has moved or is moving? Again, I don't feel it. I don't see it. Is there evidence? Let's talk about it. Supposedly, a number of millions of years in the past, all of the continents were kind of mushed together in one kind of big giant lump called Pangea or Pangaea. This is kind of what it would look like. I don't know if you can pick out any particular land masses, but this is South America, this is North America. Arizona is probably somewhere around here under the ocean. Interesting fact. Africa, Europe, and Asia. So supposedly, this is what the Earth once looked like. If we were to, again, superimpose all the countries on that previous image, again, North America, Europe, Asia, South America, Africa, Antarctica, India, way down here, which, I don't know if you know, is actually up here now, Australia, etc. So what the heck? Well, let's talk about where the true edge of a continent is. The reason being, let me go back a second. If you look at the modern day shape of the continents, some of them look like they fit together. Even if we separated this out, you can kind of see how Africa looks like it should connect to South America or North America. Some of the other ones, how do you know they go there, etc. Well, let's first talk about the true edge of a continent. The edge of our continent, for instance, the edge of North America isn't at the beach. It's not where the dry land hits the ocean. Remember, for the most part, if it's under the ocean, it's oceanic crust, this gray stuff. But the continental crust, it actually extends out a little bit under the ocean for a little while, anywhere from a mile or two up to 100 miles. The reason being is that over time, the ocean has kind of weathered and eroded, ground down the edge of the continent. So the continental crust is there, it's just been ground down a little bit. So the true edge of the continent is the end of the continental crust, which extends anywhere from, again, a mile or two up to 50, 100 miles out from where the coast actually is. So let's first keep that in mind. So how do we know at one point the continents were all together? Well, it looks like they fit together. That's how it started, but that's not really a good way to just go about it. Well, that kind of looks like it goes together. So the thing is here, let me move me, but when you look at the countries on their own, they kind of match. But when you add in the continental shelf, that's the part of the continental crust that's now under the water that's been broken down, you can actually see, like, for instance, this is all continental shelf. When you add that to South America and Africa, they actually fit together very nice. Without it, there's a little gap here. It would look like there's a little gap. So the true edge of the continent isn't where the shore is. It extends out a little bit on the continental shelf. When we start to match continents up with continental shelves, you can see the fit becomes a lot better. Right? So what else? So all right, so they match. The shape matches up. So what about the ages of rocks? If they're together, maybe they're the same age of rocks. And again, we see it looking at South America and Africa. We can see that the ages of rocks kind of match up on either sides of the continents once we put them together. Okay, so the shapes match. When we put those shapes together, the ages of the rocks match. What about geologic formations on these continents? So now looking at Africa, North America, Europe, again, when it was all together in something called Pangaea, or which means pan, all, Gea, or Gaia, Earth, goddess Earth, all Earth together. So what about geologic formations? Well, there are some mountain ranges in the eastern parts of North America, the Appalachian Mountains, that actually are the same age and type of mountains through Africa and Europe and even in Greenland. Well, how could that be? Well, then they must have all formed when these continents came together. Once you fit them all back together, you can see the formations and the ages of them all match up. Any other evidence? What about fossils? Fossils are interesting. They're kind of unique. Typically, certain organisms only live on certain continents. modern day example, koalas, kangaroos, they only live on Australia. I don't know, what do we got here in North America? What, bears? I don't know, grizzly bears, right? Those are really only found in North America. So certain animals are only found in certain areas. But if we recreate Pangea and mush all these continents together, we start to find similar fossils on a bunch of different now continents. So one of them is a Glossopteris, this kind of tongue-shaped leaf fossil. So this type of leaf fossil, plant fossil, is found on South America, Africa, India, Australia, Antarctica. All of these countries are separated. You don't really find the same trees now on these different continents, but we can find these fossils from hundreds of millions of years ago on all of these continents. Not to mention, we are finding fossils of leaves on Antarctica. There ain't no trees on Antarctica now. It's cold, it's ice, right? So what does that mean? How can we find the same fossil of an organism on different continents that way far separated? Crap, they must have been all together. So again, not only the shapes match up, the ages of rocks, formations, but also fossils. We can find similar fossils. Other fossils as well, a Mesosaurus, small little reptilian dinosaur. You can find the exact age and type of fossils in Brazil as you can in South Africa. How can that be? It must have been connected at some point. In fact, there's a number of different types of fossils. Mesosaurus, Glossopteris, Lystrosaurus. This guy, I just always point this out. Look how cute that little guy is. Look how cute that little thing is. But that fossil can be found through Africa, Madagascar, India, Antarctica. Again, there's really no organisms other than, there's penguins in them. There's a lot of living organisms on Antarctica. But just for reference, look how cute this little guy is. Oh, he's like a little puppy. Lystrosaurus. Anyway, so shapes of continents, ages of rocks, types of geologic formations, same mountain ranges, similar fossils. Anything else? There's also glacial evidence. There are things called glacial striations. Glaciers, big chunks of ice, they move. And as they move, and glaciers can be can get up to several miles thick when you go back and look through history. And even now, Antarctica is several miles thick. Greenland is several miles thick of ice. Well, this stuff moves around, and ice is very heavy. So as ice kind of moves over even solid rock, it really smooths it out and puts scratches on it, called glacial striations. So you kind of see the scratches in this rock, and they indicate the direction in which the glacier was moving. So we find glacial striations in a lot of places, but in some places that, well, there's no glaciers there now. For instance, Australia, we find all these glacial striations kind of in these directions. There's no glaciers in Australia now. It's pretty cold. India, lower southern portion of India, we see glacial striations. It's super hot there. Ain't no glaciers. Central and southern Africa, super hot here for the most part, except on some high peaks. There's no glaciers, but we see striations. Same thing with South America. We're talking about Brazil over here. So we see striations in all these places that we don't have glaciers there now. If we look at the directions of these striations, they look kind of random. But when you put the continents back together, look how they all kind of flow outward from a central position, the North Pole. I don't know if that's confused you because this is Antarctica, so Antarctica is the South Pole, but this is the North Pole? That's because North and South Pole are magnetic North and South Pole. That magnetic North and South actually flips every few million years. So at the time that this occurred, that was the North Pole at the south of the Earth. Anyway, a little fun fact. Just if you want to ignore that, but just see how once you put the continents together and we match the kind of direction of these glacial striations, they kind of all emanate from one central position. You got a central heavy mass of ice kind of just flowing out in all directions. That starts to make much more sense. So, Earth looks like this now, but we have all this evidence that points to, well, it only makes sense when you kind of fit stuff together. So what does that tell us? That the stuff used to be together. The continents used to be together in this massive continent called Pangaea. Why? The shapes of the continents, really including the continental shelves, the ages of rocks, geologic formations, all these fossils, glacial striations. So they used to be together, but now they're not. We have the evidence, but now they're not. But something is missing. What's the proof of plate movement? They used to be together, now they're not. The continents used to be together, now they're not. Well, but what's moving them? Or what's the proof of movement? Maybe they just magically just all separated. That's obviously not the case, so that proof of movement is missing. Until we discovered seafloor spreading. This actually started in the mid-1900s when submarines first started to become a thing. The Navy, the U.S. Navy, was mapping the floor of the ocean using sonar. And what they found in a number of different places, one example along the middle of the Atlantic Ocean, was this separation, this what's called the mid-ocean ridge. And there's a number of them throughout the oceans. But it looked like two kind of mountain ranges on either side of a kind of a valley. And what they quickly figured out is this is where the seafloor is actually splitting and moving apart, right along a mid-ocean ridge or rift. And that's driven by mantle convection. So as the oceanic crust is being split apart because of mantle convection underneath, all right, new kind of that mantle material, as those plates move apart, that hot mantle material makes its way up, cools to form brand new oceanic crust. So what they started to be able to do was look at ages of the rocks, look at, remember, because the north and south pole of the Earth flip every once in a while, look how the magnetic signature of the Earth was in those rocks as well. As they get further away from these mid-ocean ridges, the rocks get older, so young by close to it, older further out. You can see how on either side the magnetic field is locked in differently, but it matches up. So this is kind of what's really driving, the movement is this seafloor spreading, driven by mantle convection. What's going on underneath? Also, and that's kind of in the mid-1900s, 50s, 60s, etc. So we really didn't know how things were moving around until like 60, 70 years ago. Like your parents or grandparents, depending on how old they are, had no clue how the Earth worked. This is actually pretty recent stuff. More recent, with the advancement of technology, how do we know plates and the crust is moving around? Well, we can see it. We just use GPS. We can now see them moving around. Obviously, very, very slow. Plates move about as fast as your fingernails grow. But yeah, GPS has been a valuable tool for a number of different things, not just finding your way on a map or whatever, but we can also use it to track plate movements and ground movements. Points on the same plate move generally in the same direction. But what's interesting, that North America, you can see for the most part, is moving down and to the left, but this portion of North America is moving up and to the left. It's because part of North America is on part of the United States, part of California is actually on a different plate, the Pacific plate, where most of the United States is on the North American plate. So we have evidence of Pangaea, meaning we have evidence that plates are together now. Plates were together millions of years ago. They're not now, so they must have moved. How did they move? Seafloor spreading detected that. GPS helped us to detect that as well. So they're continuing to move now. So what are they going to look like 150 million years in the future? Kind of like this. Africa's cruising north right now, crashing into Europe. It's going to kind of kick it up while Asia's kind of drop down. Australia and Antarctica are going to kind of crash together. Again, North America is kind of moving down in the general, down and to the left, but parts of California are moving up and to the left. So how do we know this? We can just see how fast and the direction everything's moving now, all these different plates. We just kind of hit fast forward and see what happens. So if you're around 150 million years, there's your map. Let's pause here. When we come back, we'll talk about how the plates move a little bit and the motion of plates. See you back here in just a second.